So got one more week and then a week off. So we'll try to get through sampling distributions this week. So I know one part of the time it's frustrating right now in the course is like I gotta give you a bunch of different tools before we can do some stuff that I think makes a little bit more sense and also kind of is a lot more powerful. So we'll kind of keep building up that toolbox today. I think in fact, first thing we're going to start with is I have this Indiana weather blank file up under the files in class data folder on Canvas. So we're going to open that up. We're going to kind of work with that. Also, just to make sure people are aware, I also put in the exam and the answer key in a folder up here on Canvas. So you can kind of take a look at that. Other than that, we've got the connect assignment, which I would try to chip away at as much of this as possible this week. Because if you try to do this after we come back from spring break, it'll be pretty far removed from the material, right? Or at least for some of the early questions. Okay? And then we'll start with this Indiana weather blank file. Okay? So I'm going to try to show you what we did last class, how we do that in Excel. We'll then kind of go back, talk about inverse transformation, and I'll show you how we do that in Excel as well. So we kind of ping pong a little bit here today. So if I go to this temp normal, and then I'm gonna zoom in so we can see what I'm doing. I've got this set up. So I had all this historical kind of Indiana weather data by year and then by month, right? So all I did over here, move this around, is I found the average of the kind of whole year's temperature. I did the average of June, July, September. So this is kind of my mean. I then found the variance, right? That's just using that var.s. And then I found my standard deviation, which was just taking the square root of the variance, right? So we kind of already had that in there. And then I just had these hypothetical kind of cutoff values, right? So what we were doing last class, this first one, we'll think about this random variable, which is June temperature. We said temperature is pretty normally distributed. And it should be centered around that mean that we have of 70.86. I'm then going to say, okay, look, what's the probability that I see 71.4 or anything below that? All right. We said, how can we figure out what that is? We're going to convert our normally distributed variable into a standard normal distribution by using our equation for the z value, right? Once I have that z value, I can look it up in the table, and the table will give me the area to the left. Okay? So that was kind of the process we're doing. So we'll see, how do we do that in Excel? So the first way I'll show you how to do it is we're simply going to use Excel to be our calculator. We've got the mean, we've got the standard deviation up here, we have the cutoff value of 71.4 we're interested in. So I'm just going to take that x value, subtract the mean for this variable of June temperature, and then divide by my standard deviation. Just using Excel, just like a calculator, right? But instead of typing the numbers, then I'm just clicking on where those numbers are at. Any questions on their method? So once I have that z value in practice, well, first of all, before I hit enter here, what can I say about this z value? It's going to be, so we think about, what will the z-score for the mean always be? How many standard deviations away is from the mean is the mean? 0, right? So if I then want something that a cutoff value to the right, that's going to be a positive z value, right? Or a certain number of standard deviations above, right? Now, if I'm looking at this, mean only what, like 0.6 away from the mean? My standard deviation is 2.5. So I'm like way less than 1 standard deviation away, right? Just thinking about this initially, I'm thinking, oh, this is probably going to be something like, I don't know, 0.3 or something pretty low. So with a z value as low as like 0.3, I'm starting to get pretty close to that z value of 0, which means this area is probably a lot closer to 0.5 than it would be to 1, right? If instead I had seen something, I was using like 80, well, now I'm several standard deviations above the mean, now it's likely that the area to the left is going to be a lot closer to 1 than it would be to 0.5. So hit enter, sure enough, about 0.21. Okay. So I've got my Z value. In practice, what I would then do is go to my table, find 0.21, my Z value, and then grab that corresponding area to the left, or probability of seeing that value or anything below it, from the table in the middle. Okay. So that was like last week we said, okay, 0.21, 0.5832 would be that area to the left. But I don't want to use this. I want to use Excel, right? So in Excel, if we use the norm.s.dist function, this tells Excel, hey, look, I'm using a standard normal distribution. I'm working with Z values, right? I'm going to tell you a Z value, which is right here, and then comma. I kind of introduced another function last week and said we're always going to use the cumulative. I mean, the 0 doesn't do anything for us. I don't even know, like I said, I don't know what it even gets used for. We're always going to use kind of find these cumulative probabilities. Okay. So this is essentially going to look up like a stored table in Excel and find that same value that we just looked up in the table, right? So I hit enter, and it's a little bit off from what we just looked up in the table, like out to the third decimal. So that's because when we're using the physical table, we're constrained to 2 decimals, right? I looked up 0.21 before. Well, the actual Z value is a little bit, a bit larger, right? So Excel is not constrained to 2 decimals. It doesn't have like a built-in table, actually. It's doing the integration for us. So it can give us a little bit more of a precise answer. Okay. Any questions over anything there? You want to see a cell again? Okay. So I introduced this function last class, though, just to kind of show you how we don't have to break this down step by step. I did this just to kind of show you, right? It also allows us to see how many standard deviations where we were. It also matches up how we do this by hand, right? But if I want to skip a bunch of steps and have Excel do the work for me, I can use this not norm.s.dist, but just the norm.dist function. So this tells Excel, okay, look, I'm dealing with a normally distributed variable, not standard normally distributed. I'm interested in finding the area to the left of this cutoff value, comma, here's the mean of this normally distributed variable, comma, here's the standard deviation of this normally distributed variable, and then just like before, comma 1, always making it cumulative. So I've given Excel the cutoff value, the mean, the standard deviation. That's everything it needs. It calculates the Z value for you behind the scenes. Basically then throws it into the norm.s.dist function, integrates or finds the area to the left of that value, and then spits back out the probability. So it kind of does everything that we just did before. So hopefully it should give us that same probability of 0.58. You just did it all behind the scenes. Okay. So in practice, like if you're looking at, I'll probably get an Excel assignment up there this afternoon. It'll be a due date way down the road because part of it will be stuff we do after spring break. But the very first part of it might be doing something simple like this. You don't have to break this down by step. You can just go straight to the norm.dist function in practice, right? I was just showing you the other way because I don't know, it's easier to like trace down your errors a little bit more if you kind of break things up into steps. Questions on that? Want to see a cell again or? Okay. All right. So, just to kind of show also, I could just copy this over. Now it kind of is the same thing for the other 2 months that I had up here. I could play around with my cutoff values, right? Notice this is like basically 0. Kind of makes sense. What's the probability the average temperature in July is 56 or below? But we could play around with, you could play around with different cutoff values, and these will kind of update for us. So one thing that is kind of annoying is that there's not an option to just do this in our norm.dist function. But let's say instead I want to know what's the probability that I'm above a certain value. What's the only other thing I should have to do? If this norm.dist function, just like the table is giving me the area to the left, if I want the area to the right, yeah, so someone else, 1 minus. So unfortunately, there's no like option to give me the area to the right from these norm.dist functions. So I can kind of do just do 1 minus, right? I think that kind of gives me the probability of seeing that value above. Now, just to make a point, I don't have to break this down into steps either. So I could do this all in one cell where I say, okay, look, I know that I want the area to the right. So that's going to be 1 minus whatever the area to the left is. Well, how do I find the area to the left? Well, that's that norm.dist function. I want to find, my cutoff values right here, comma, here's my mean, comma, here's my standard deviation, comma 1. Right? So this will do it all in the same cell. I don't have to break it up into steps, and I should get the exact same value that I had. Questions over anything here? I'll do one more thing that's a little bit harder. So let's say, I'll try to keep my examples the same to both classes. I think this is the one I used. So let's say instead, I want the probability that I'm in between two values. So we did a couple examples like this by hand. In fact, I'm going to create something else next time that I didn't do for the first section. But I think it might be useful. So let's say I wanted the probability I'm in between two values, right? We said if I'm doing this by hand, I would need to turn these into z values. I'm just going to call this z1 and z2, right? Then I would look those up in the table. Table would give me the area to the left of my first z value. I could then look up the area to the left of my second z value. If I just want to know what's the area in between, all I do is subtract that smaller area from the larger area. Okay. Well, I can do this in Excel, right? All I need to do is find two areas to the left. So I could do, well, norm.dist, right? That first, or the higher cutoff value I'm looking at is 71, comma, here's my mean, comma, here's my standard deviation, comma 1. This will give me the area to the left of that cutoff value of 71. Calculates that z value. I don't even have to see that, right? It calculates behind the scenes for me. I would then subtract from that the norm.dist function, where I'm looking at the lower cutoff value, right? So 68, I think is what I was doing, comma, here's the mean, here's the standard deviation, and then kind of putting a 1 there to make it cumulative. So I can do this all in one cell too. Like I said, you can break it down if it makes it easier to kind of track what you're doing. You can do it all in one cell. Now, one thing I'll mention is you always put the higher end of your interval first, right? Because you're always going to want to have this higher area or larger area and subtract the smaller. Well, that means that you have to put that higher cutoff value first, and then the second cutoff value will go second. Now, if I forget to do that, so I hit enter here just to show you it can work. But let's say I screwed up. And I don't know, I did this, right? I flip-flopped. Hopefully, if I think about what I'm doing, wanting the probability I'm in between these two values, if I see this, why do I know I made a mistake? I'm looking at a probability. It has to be between 0 and 1. Oh yeah, probably the mistake I made was I was actually subtracting the larger area from the smaller area here. So that's gonna kind of give me a negative value. It's because I should have been putting the higher cutoff value first and the other cutoff value second. Okay. Any questions over anything there? Let's see something again. Okay. Let me think. I think this is could be cool. So let's say use that norm.dist function. This is going to be kind of weird. And I probably won't push you this far in the homework, but I think this will get a point across. I think that it's good. So let's say I take the mean and I just add the standard deviation to it, right? That's the X value I want. So really what I did there was I'm saying that cutoff value I'm interested in is 1 standard deviation above the mean, whatever that ends up being. My second one, I'm going to go 1 standard deviation below, right? So I can then use the table, find the area to the left of 1 standard deviation above, find the area to the left of 1 standard deviation below, subtract the smaller from the larger one. And if we remember, what number should I get here? probability I was in between one standard deviation of the mean should always be about 68%. So let's see if that's true, right? So my cutoff value is one standard deviation above the mean. I then need to tell it, well, here's my mean, comma, here's my standard deviation, comma 1. Right? I then subtract from that. I want it to go one standard deviation below the mean. So that's my second X value, right? One standard deviation below the mean. Tell it that variable's mean, comma, standard deviation, comma 1. Hopefully when I hit enter here, I should get, I think it's like 68.3%. Yeah, 0.682 something. Right? So you could, like I said, you do 2 standard deviations, 3, we kind of proved to ourselves that these will always be, you know, whatever I said, I think it's 99.5 and then 99.7 or something. But it's kind of using all these elements that we've kind of been looking at and just taking the area to the left of the higher cutoff value, subtracting the area to the left of that lower cutoff value gives us the probability of being in between those two. Okay. Any questions on that before we keep going here? All right. So we'll ping pong back to the slides here. Oops. So I have this up here so you can see it, but I'll kind of hopefully give you a better idea of what we're doing here. A little more of an explanation on the board. So we were just doing a process where we had a cutoff value. We turned it into a Z value and then found the area to the left, right? So the inverse of that, we're like going to be working kind of backwards, would be something similar to the following. Let's say I've got some tests and I know it's a normally distributed test. So like you write a good test, it should be pretty normally distributed. And let's say this one was, and I want to find, I want to find the cutoff score for this exam or this test score. That's the 90th percentile, or better than 90% of the other scores. So that's why I think we talked a little bit about percentiles earlier in the semester. I wasn't going to make expect to know because basically we've got a better way of doing it. This is the way, right? We're dealing with a truly continuous variable. If I want to know the 90th percentile for this cutoff score, well, then I'm thinking there's an area of 0.9 to the left. Right? So how can I find this? Well, I know that whatever this cutoff score is for this exam, right? What if it's 89 or 93, whatever it ends up being, that 90th percentile, it would be a certain number of standard deviations away from the mean, right? I could turn it into a Z value, right? If I had the mean and the standard deviation. I know whatever Z value that is, well, that would give me that desired area of 0.9, right? Whatever this cutoff score is, the area to the left of it is 0.9. When I turn it into a Z score, the area to the left will be 0.9. Okay? So I'm now starting with that area in the tail, or I have my probability. I'm then going to take that probability, look up my Z value. Right? I'm then going to take my Z score formula. I'm now going to know my Z value. I can calculate the mean and the standard deviation from my data and trying to find what cutoff score corresponds to that. So I just rearrange this a little bit with algebra, and I get this inverse transformation formula that I can calculate the mean and the standard deviation from my data. All I need to do is figure out what's that Z value that corresponds with that area I want in the tail, 0.9. So how do I do that? So I go to my table here. Before we were looking up a Z value, right? We had it, we knew what it was. Well, now we know the area in the tail, or essentially the number that we have, 0.9, is going to be what we want to try to find in the middle here. We want to think about it this way, like every Z value has a corresponding area in the tail. It's always going to be the exact same, right? If I look up a Z value of negative 1.2, it's always going to have that exact same area to the left, right? So if I want the area to the left of this tail, or in this left tail to be 0.9, it's going to have a corresponding Z value, right? That would always go with 0.9. So I scroll down here and I try to find the value in the middle that's the closest to 0.9 as I can get. So it looks like I'm in between these two, right? Or if I'm in between these two, I would say, okay, look, that corresponds to a Z value of 1.28 and 1.29, somewhere in between there. I'm constrained to 2 decimals. So what we're going to do in practice, anytime we are in between two, we'll just take the larger or the higher magnitude. We're dealing with negative values. This means like if I have negative 1.2, 1 and negative 1.22, I take negative 1.22, right? The higher magnitude value. So we were in between, right? If we wanted that area of 0.9, we were in between these two values, and the corresponding z values would be 1.28 and 1.29. So we'll use the higher of the two, or we know that in order to get that area of 0.9 in that left tail, I need to be looking at a score that corresponds to being 1.29 standard deviations above the mean. Well, that's all the inverse transformation formula is doing for me. It's saying, okay, look, take whatever the mean is, add to it 1.29, right? That's my z value now. Standard deviations, right? Multiply the standard deviation by 1.29, add that to the mean. That's the cutoff score that gives you 0.9 in the tail of it, right? So we're working in the reverse, basically, right? Before, we started with a cutoff value, turned it into a z score, then found the probability or the cumulative probability of the area to the left in the table. Now, we're starting out with the area to the left, right? Or that cumulative probability, finding its corresponding z value, then using that to find that cutoff score. So we're just working kind of backwards, right? Any questions on this before we go through? I'll go through an actual example with some numbers here. Okay, so I think I hopefully have this matched up. There we go. So we just looked this up, but let's say I had, oops, sorry, skip my example. There we go. Let's say I had this test score, and I know that the mean is 72, and my variance is 64, right? Well, once I get to my inverse transformation formula, I need the standard deviation, so I'm just going to go ahead and calculate that now. So that's just the square root of 64, or the square root of the variance. So I've got a mean of 72, standard deviation of 8. Okay? If I want to know what test score value would be kind of the cutoff for that top 10%, or said differently, be better than 9% of the other scores, I now know the area I want in the tail, 0.9, right? I would look it up in the table the way we just did. We found that z value is 1.29. Now it's just a matter of plugging everything in. I've got my mean of 72. I've got that z value I found from the table. It gives me 0.9 in that left tail. And I have my standard deviation. So it's just a matter of plugging those in. And I can figure out that this cutoff score is what, 82.34. So if I got an 82 in this class, I'd be kind of about better than 90% of the other test scores. Right? That's not specific to this class. I think it's for the example. Any questions on that? We'll go through another one. So same setup, but now I'm working with, I want to know, well, I didn't do very hot on this exam. So what's the likelihood I was better than 40% of the other test scores, right? What score would I need to get to be better than 40%? So we're starting out, we've got this normally distributed test score. We know its mean, we know its standard deviation. Now right away, so I can draw the whole thing out. So we're gonna, I know that I want to find the test score that gives me an area of 0.4 in that left tail. Why did I know that that cutoff score that I'm looking for has to be below the mean? So if the area I want in that lower left tail is 0.4, what's the area to the left of the mean? 0.5. So if I want something smaller than that, I've got to be looking at a score that's to the left of that mean. Right? So that would also tell me what's going to be true about my z value that I find that corresponds to an area of 0.4 to the left tail. Has to be negative. I can actually even say a little bit more. Well, no, I can't. Sorry, I'll jump in the gun. No, that's all I can say right now. So we know that it's going to be negative, right? So if I look up here, remember, I have to find the z-score as part of my process, but what I'm actually looking for is what is that cutoff score. So I know that cutoff score has to be below 72. I can rule out B. But then just think about, I'm looking for the cutoff score of the bottom 40% of a test. 0.26 and negative 0.26 doesn't make a lot of sense, right? Unless it's like the, which one is it that penalizes you for getting it wrong, ACP or SAP, one of them. Negative values don't make sense here. I'm going to assume that when we actually figure out what this z value is, probably negative 0.26. So I want this area on the tail to be 0.4. I need to find that corresponding Z value. So I go to my table, scroll down, looks like 0.4 in between these two values. All right, it's as close as I can get. So the corresponding Z value for that area of 0.4, negative 0.2, scroll up, negative 0.25 and negative 0.26. So we're anytime we're in between two values, we'll use the larger of the two, right? Or the whatever value is larger in magnitude. Any questions about how I found that Z value? So it's exact, before we were using the row and column headings because we knew the Z value and we wanted to find the corresponding area in the tail. Now we know the area in the tail, and then we go over and up to find what that corresponding Z value is. You could almost, if we didn't want to use this table, yeah, you could actually write out like, think about this way, it's like what, negative 2.9, 0 always has an area of 0.0013, negative 0.291, right? It doesn't look any different in the fourth decimal. You could essentially take every Z value that you could look up on this table and write right next to it the area in the tail. The only reason why we display it in this table is because if you do this, you're going to have like a really, really, really long, you'll have several sheets. So this is kind of a way you kind of show that all kind of quickly. But I guess what I'm trying to get at here is every Z value has a corresponding area in the tail, and it's always going to be the same, right? So if I want a certain area in the tail, I'm always going to find the same Z value. No matter what example I'm doing, if I want an area of 0.4 in the tail, I'm always going to have to use that Z value of negative 0.26. And so once we get to things later on, like confidence intervals, we'll start seeing like the same Z values start popping up a lot. Because if we have benchmarks like 90%, 95%, when we look up these values of 0.9, that area in the tail of 0.9 or 0.95, we're always going to find the same Z values. We're not done yet though. All right, we're just finding that Z value. The next thing that we have to do is use that inverse transformation formula. Well, I've got my standard deviation of 8, my mean of 72. My Z value I just found was negative 0.26. All right, so get everything plugged in. And we get 69.92. Questions kind of on this inverse transform? Yeah. Yeah, that'll be one of the formulas on the formula sheet. Any other questions? Yeah, you know what? I might just put the formula sheet up for the next exam, just so as we work through stuff, you can kind of see like what, I mean, I try to put every formula that you'll need on there. So, but you can kind of get an idea what that looks like. All right. Let's take a look at how we do this in Excel. So I'm going to go back to this blank. Here's the inverse transformation worksheet. We're going to kind of basically use the same example that we just had. I'm just going to show you how we do it in Excel. Okay? So we'll start out with the area that we want in the tail was 0.4. Right? We've got the mean of our test was 72. The variance was 64. Okay. If I wanted to find, I'm going to start with the alternative way first because that matches up with how we do it by hand. I'll then show you a shortcut. So norm dot, s dot, oh no, sorry, I'm lying to you. Norm dot s dot inv. So just like I had the norm dot s dot dist function, that's where I told it a Z value and it gave me the corresponding area in the tail. Norm dot s dot inv, I'm telling it the area in the tail, and it's going to give me the corresponding Z value, right? So it's basically going to do what we were just doing, right? Look up that area of 0.4, see that the corresponding Z value is negative 0.26. So here, I'm just going to click on the 0.4 instead of typing it in. And sure enough, I get about negative 0.26. Now, it's a little bit different because in Excel, we're not constrained to 2 decimals, right? We need a little bit more precise, right? Before, remember, 0.9 was in between 2 values. So this is what the actual Z value would have been. Questions there? So once we have the Z value, well, now I'm just going to use Excel to be my calculator. Take that mean, add to it whatever the Z value is, times my standard deviation. Well, I don't have my standard deviation, I have my variance. So what can I do? Just going to use the square root function and then click on my variance there. Okay. So I'm just using Excel to be a calculator at this. Imagine how I would do this like. So hopefully, if we get this right, we should get, didn't write it down, whatever it was, 69 point something. 69.97. Yeah. A little bit different than what we thought. I think I had in the slides. But once again, because we can be a little more precise. We're not constrained to 2000. Okay. Any questions before we keep moving? Let's see a cell again. All right. So let me show you the quicker way. So just like where we have the norm.s.dist, and we could break it down by steps, we said, well, norm.dist does all the work behind the scenes for us. Similarly, instead of using that norm.s.inv to kind of match up with how we would have to do it by hand, we could use just the norm.inv, which essentially says, okay, look, what area do you want in the tail? So what's that probability that you want? 0.4. What's the mean of your normally distributed variable, comma, what's the standard deviation? Once again, probably should have just calculated the standard deviation in a different cell, so I keep clicking on that, and not having to type in the square root of the variance every time I want to use the standard deviation. So you'll notice like these norm.dist, norm.inv functions, they always want the standard deviation. So it probably is better practice than what I'm doing here to like also have a cell where you just put the standard deviation there, so it's a little bit easier to just click on it. Any questions? So hopefully this is going to give me the exact same test score. So what this is going to do is say, okay, look, I know the area that you want the tail is 0.4. I'll figure out what that corresponding z value is. Hold on to that. You told me the mean and the standard deviation. Well, that's all I needed to kind of throw into my inverse transformation formula so that it can spit back out at you what that actual cutoff score would be, right? Whatever that test score would be. Sure enough, you get the exact same thing as if we broke it down by steps. Questions on that before we keep going? Yeah. Down here? Yeah. So there, I'm basically just using Excel to be my calculator. Yep. I don't have like a built-in function for that because I mean, in practice, like no, why would you do this when you could just simplify and do that? But it's I also do things like this in Excel because it helps me. I like to see things like line by line, and also then I can figure out if I made a mistake somewhere, like what did I actually go wrong? Whereas if it's like all in one cell or it's doing stuff behind the scenes, I can't see that. But when it comes to like the Excel homework, by all means, go right to the one that does the work behind the scenes for you. I'm just going to show you this so we can kind of match up with the concepts we already talked about by hand. Questions before we keep going here. All right. So, you could play around with different cutoff scores. If we go 0.9, we kind of find what we had before. Notice, we're a little more precise. We're in between 1.28 and 1.29. We can get the exact Z value. The other thing just worth mentioning, if I put 0.5 in here, what should the test score be that gives me it's better than 50% of the other test scores? So if I wanted the area of 0.5, what Z value will always give me an area of 0.5 to the left? Yeah, saw someone hold it up, 0, right? The mean always has a Z score of 0, and it exactly splits my distribution in half. So if I put 0.5 in here, the Z value I'm going to be looking at is 0. 0 times anything is 0, and I'm left with just the mean of 72. But one thing you could do in practice, like you kind of already know what the mean is, the median for these normally distributed variables, but just to relate to the other things we've talked about, you could very quickly, and you could do like this multiple cells that you had all the numbers right in front of you, but I could find the 25th, the 50th, and the 75th percentile, and then I would have all those values I need to kind of build those box and whisker plots. Right? So in practice like that would be how you could use this to kind of just, do those box and whisker plots that we kind of talked about a long time ago. I'm not going to make it do those. I'm just pointing it out for in case some other classes start to introduce this idea. This would be kind of how you do it, right? You would then have your first, third, second quartile, and then it would just matter of figuring out your lower and upper limit. All right. So here's some, I guess, summary of kind of what we did. This kind of like has just a more general form of how you use that norm.dist and how you use that norm.inv function. Skip this for now. And we will talk a little bit about sampling today. We'll have to finish up the discussion on Wednesday. I don't think we'll have enough time. But everything we've been doing, notice I've been using population means and population standard deviations. We've talked already before, we usually don't have population data, right? So we won't really deal with the infinite populations too much, although it's really approach it the same way we would these finite populations. The problem is we usually don't have population data, right? Maybe from the census, but they only do that every 10 years. It's kind of hard to make sure that we've got guaranteed every single person responded. So we usually only have sample data, right? So then what we're going to have to do is take that sample data, right? I might be interested in what the population mean is, but all I have is my sample mean, right? So I'm going to use that sample mean to make inferences about the population as a whole. So the problem is, when I'm taking a sample, we can run into some things that might bias our sample. So we'll start to talk about bias, how we eliminate it today a little bit, and then more so on Wednesday, talk about how we identify where the bias is coming from. So we're going to have some population, capital N. We'll have a small subset of that for our sample, lowercase n. We've already used this. You can do with or without replacement. I say it's better. I guess it's kind of a subjective statement. But 99% of the time, you should be sampling without replacement. So with replacement mean, let's say I'm interested in, I don't know, the average test score in this class, and I don't have any idea what they are. Got all your names in a hat. I draw out one name, write that person's test score down. Put that back in the hat. Shuffled up, draw another name, write that person's test score down. What's the problem if I do that? Let's say I'm only going to randomly sample 10 of you. If I'm putting the names back in, I could end up with the same person twice, which that's a problem because now when I'm calculating my sample mean, everybody is 1 out of however many observations, but that one person is 2 out of, right? They're being overweighted, right? So like I said, there are cases where with replacement might make sense. Like if you're thinking about something where you could see someone make multiple purchases, so it's okay if you get them in your data set more, but 99% of the time without replacement is better, right? So, and I won't waste time with that because we're not going to really deal with infinite populations too much. I wanted to make sure we get to today talking about stratified and cluster random sampling. So I randomly sample, right? Maybe I'm interested in, let's say, okay, I know I have to set this example up. So let's say I'm interested in human height, right? And I sample 10 people, right? Randomly, just start choosing people at random from the US population. So somehow I have a list that I'm going from. And I somehow end up with 8 males and 2 females in that data set. If I'm interested in the average height in the US, why is that going to be a problem? If I end up with 8 males, 2 females, and then calculate their average height, so that's my sample mean. What's probably going to be true about that sample mean relative to the population mean height? Going to be higher, right? Because I know that the population has about 50-50, right? 50% male, 50% female. Because that's a little off, but you get the idea, right? So what do I want to guarantee that my sample has? About 50% male and about 50% female. If I want that sample mean to truly be reflective of what the population mean is, right? Now, that's kind of a trivial example. But the way we're going to do that is we're still going to randomly sample, right? We don't want to cherry pick who's in there, but we're going to break our population up into these different subgroups. In my example, it was just male, female, right? We're then going to randomly sample from each one of these subgroups or these stratum. So in my example would be randomly sample 5 males, randomly sample 5 females, then throw them together to get my now full sample. Now I've got a sample that I know is reflective of kind of the gender breakdown of the population. And this really only matters if these characteristics are kind of correlated with the variable I'm interested in. So that's why I used human height and gender. If I thought about the same thing, and I'm like, I don't know, I'm interested in IQ levels. It's the same across the genders, and so it doesn't really matter what my makeup looks like in my data set, right? Because that variable, right, gender would not be related at all to the IQ measure. But in the example of height, I would want to make sure my sample looks similar to the population on that characteristic of gender. that make sense? Anything in there? So just some other examples that we'll often see in different kind of division. Sometimes we'll break it down to like income. I want to make sure that like my sample has an income distribution that looks pretty similar to the US. Like I don't want to have, if I had a sample and it was small, this usually matters more with small samples, right? Because I only have like 10 people, unless that accidentally, I don't accidentally, I just randomly sample and I happen to get 5 people that make over $300,000. Well, I know my sample mean isn't going to look like the true population income for the US in that case. So maybe I kind of guarantee I'm only something like one person to be one of these income brackets. Age is another one, right? Anything that's like demographic breakdown that we might want to make sure our sample looks very similar to our population. Okay. Another very closely related idea is cluster random sampling. So with cluster random sampling, it's going to be the same thing. We're going to kind of divide it up into subgroups, but these subgroups are just going to be like smaller scale versions. It doesn't like separate people up by characteristics. So 99% of the time with cluster random sampling, the only difference is that we're doing this by geography, right? So it's the same idea, same setup. We break this down to like different areas. So I'll give you an example. Let's say I'm interested in predicting the popular vote for the presidential election. I randomly sample 100 people, and I just so happen to end up with 2 people from every state. If I'm interested in just the popular vote, why is that a problem? Because I know there's way more people in California than there is in Delaware, right? So I shouldn't have the same number. I want my sample to be reflective of whatever that population looks like. So I might break it up and say, okay, look, I'm going to take 15 people from California, 1 person from Delaware, 3 people from Indiana, right? And try to choose a number that kind of corresponds to whatever their percent of the total population is, right? Once I randomly sample from all these states, kind of match up with, the percent of the country they are, I'll then throw those all together, and that'll be my full sample. Now, it's still random. It's just guaranteeing that this random sample now has kind of a state representation that matches up with the population as a whole. So it's the same idea. It's just we're not doing it by a characteristic. We're usually doing it by some geography, right? Questions on that? Shouldn't be too bad. So I just want to introduce these ideas today, kind of to start thinking about bias. One kind of real practical application of this I kind of already mentioned is like political polling. So anytime you see the political polls, if they're trying to give you a popular vote prediction, right? They should be using something like cluster random sampling, right? To kind of guarantee that they're going to have, more people from California in their sample than they are from Delaware, right? In fact, once we get, I don't think we'll get there until after spring break, but I think it might be the first class after spring break, we'll start talking about confidence intervals, and we'll start actually going through and seeing how we can actually make predictions for these elections, right? But for now, we're just thinking about some of the bias that we want to try to eliminate and trying to make sure that our sample is representative of the population as much as we possibly can while still keeping it random. Okay. Any questions before I keep going here? Got one more thing to end. So I'll go back here. I skipped it. There we go. So I had this data laying around. I just always think it's cool when I see stuff like this. That's probably lame, but it was this powerlifting data set. And so I was just looking at one lift specifically just to make the point. So it was the deadlift. I mean, these are pretty, this may be a little bit of a skew here to the right, but these are really close to normal distributions, right? And, like I said, looking at like a lot of human performance or biostatistics, it's just, they always end up looking normally distributed. So we looked here just to kind of make a point of how we can use data maybe to tell things that were to lie, or also how we can use data to then actually prove very interesting points. You could take this and someone say, well, look, men are way stronger than women, right? The average weight lifted here is like 600 kilograms versus 300 or something, right? Okay, yeah, you could say that, but I looked at the data and I can guarantee you there are a lot more 300 plus pound men in that data set than there were 300 plus pound women, right? So yeah, they did lift almost twice as much. They also weighed twice as much if we're looking at the average weight of the lifter. So I always had this idea, like you could take 2 people, male, female, same exact height, same exact weight, same exact structural build. They're going to be the exact same. Muscle fiber is muscle fiber, right? So we can start to maybe control for these other factors. My guess was always like, yeah, strength is the same between the 2 genders, right? It's just that Men typically are taller than women, right? So you just account for the one factor, which is body weight. So I took the total amount of weight they lifted and divided by their body weight. So essentially getting like a per pound body weight or per pound lifted for their body weight. Call this the Wilson powerlifting. Closer than that. What you notice here is still normally distributed, right? The average kind of for males, I don't know, somewhere 350 below 400. Average for females right around that same value, right? In fact, if you can kind of control for height, which we can't just do with these probability distributions, but eventually we'll get to something called regression. What you end up seeing is as long as you control for height and weight, per pound lifted is like no different between men and women. So you could start out, you know, being an idiot and using the wrong statistic to try to make some asinine statement. But if we kind of think about the situation, right, and we just control for one factor, we then get a completely different story, right? And hopefully, like once we get down to the end of the class, we do some linear regression, we can really show like we can control for not just body weight, we can control for height, we can control for age, all these different things. But this is just kind of a quick kind of look at that before we get too far down the road. So we will continue talking about bias on Wednesday. We'll then start talking about sampling distributions. I would start trying to chip away at that connect assignment so that we don't get too far removed from that material. You know, once you come back from spring break. Other than that, try to stay dry out there, and I will see you on Wednesday.